There we go. And they now have alibis for this time. Perfect. We were right on schedule.
Someone had the audacity to imply that I don't have enough class videos.
Ooh. Some random student?
No. Did I say that right? I had the audacity to claim that I had too many class videos. I think that's the opposite of what I just said, isn't it?
I think you said someone claimed you not enough,
Yeah, no, the opposite of that.
which makes no sense because you just said that.
Does anyone ever actually go back and look at the old ones?
Some of them.
I said, I don't. Though I tell myself, before the semester begins, I should get a view count just to see how many people watch anything. All right. What can you tell me about the atom?
There's a lot. And it's really tiny and they are made of, or they have electrons, I think.
They have electrons. Sure, we'll pretend. And?
Protons.
Okay.
And a nucleus.
And a nucleus?
Neutrons. I don't think that's like nuclear.
There is a nucleus.
Oh, okay, I was right. What is made up of those things?
Proton, the nucleus is made of
Yeah.
protons and the neutrons,
Yeah. And the
it's
electrons go around.
surrounded by my fault. Then it's surrounded by a cloud of electrons, if you will. Something like that.
Yeah, something like that. There we go. Oh, no, that's not what I wanted. Like that. Okay. So we got these three things. There's this nucleus, and the electrons go around it. Sort of. The planetary model of atoms is well, that was the thought at one point. Actually, electrons could be in the nucleus or outside the nucleus. The cloud makes it seem like there's this mist of electrons. And it really comes down to where is an electron? Well, it depends on how you look at it. If you look at it one way, you can find a specific location. You look at it another way, you have no idea where it is. And there's a certain probability it's in the nucleus. But all that stuff, if we get to that level of sophistication, will happen at the end of the course. What can you tell me about electrons? Besides, they tend to hover outside the nucleus.
They have a negative charge.
All right. Protons?
Positive.
Neutrons?
Neutral. Charge.
What goes into neutrons? Neutrons and protons are not fundamental particles.
Quarks.
Yep. So these two things are made up of quarks. Though we've never seen an individual quark before. Trouble is that quarks are bound so tightly to other quarks that if you rip them apart, so much energy is released it produces another pair of quarks. So you never actually get a quark by itself. All right.
What is a quark?
It's a particle it's a fundamental particle that's not broken up anymore.
Yeah.
Or maybe it is. Depends on which theory you're listening to. There is someone who actually came up with another theory that quarks were made up of these more fundamental particles, which they called prions, not the same as the biology ones. But we have no experiment to know if he's right or not, which is what basically what theorists do. They create a whole bunch of 99% crap and let history decide whether they're geniuses or not. All right, so what do we know about negative, positive, and neutral charges?
They interact with each other differently.
Please go on.
The positive and negative attract. The negative net, like the same sign repel each other. And the positive charges, the same sign charges repel each other, and then the opposite sign charges stick together.
Okay, opposites attract, like repels.
Yes.
All right, so as we go through this whole bit of, well, in essence, electrostatics and beginning electrodynamics, there's two fundamental rules that really you should keep in mind. Rule number one, opposites attract. Like repels, that's one thing. And number two, 99.9+% of the time, the electrons move. The number of times I've had students tell me it's the protons that are moving. If I want to move protons, let's say I have protons in this desk. If I want to move protons, here's how I do it. Protons will move, just because everything moved. But if we're talking about electricity, it's the electrons that are moving, and pretty much everything that you do, with possible exception of any of you pursue physics far enough, or some aspects of engineering, then you can't have protons move. So how do you get a proton or an electron? I mean, there's atoms all around us, there's protons there, but how do we isolate a proton?
You take the nucleus, and you look at the orange ones.
Okay.
The orange ones are the protons. Just take those puppies out, and then you deal with it.
Okay, there you go. Physicists have been doing it the hard way for so long. What's the purpose of a neutron?
To hold each other.
All right, so I got a nucleus. What's in the nucleus?
Neutron is attract protons.
Okay. So I got all these protons in there, and they hate each other, despise each other with a passion. They just want to get as far away from each other as possible. They don't want to come towards each other and fight, they just want to run away.
So neutrons are
Peacemakers.
peacemakers.
In a sense, yes. There is another force involved there that, for electric forces, opposites attract like repels, but there is another force called the strong force, which basically keeps the nucleus from flying apart, and neutrons are a big part of that. They also serve as keeping protons separated from each other. Now, this is the point where I would point to a periodic table, but apparently no one cares about periodic tables at the moment except for me. Except for us. Sorry, all of us care. But again, I'm gonna have to ask you to reach back into the depths of knowledge and tell me, are neutrons necessary for all atoms?
Yes. You said neutrons or protons?
Neutrons.
No.
Okay, that's probably a decent guess. Can you back that up?
I think there's one element on the periodic table that only is made up of one proton.
What is that?
Is it helium or hydrogen?
Hydrogen.
All right, so I have a hydrogen with one proton. It is generally neutral, so I have to have just as many electrons. I'm just talking just generic hydrogen. All I have to do is apply enough force to the electron to rip it away, and I'm left with a proton. Now, what's required to rip it away? We'll get to that. So I have here an electroscope. This little disc right here is, I suspect, bakelite. It's an insulator so that any charges, unless I soup it up really, really far. Rotate that. So charges, if I put any charge here, it's going to run through, or if I'm pulling any charges out, it's going to come out through here. It's not going to go into the case. Now, I guess the question is, can everyone see the two flimsy bits of metal inside the leaves? All right. That's it for today. All right, so I take some rabbit fur, and for those of you concerned about the rabbits, they did not need their pelts because they were all moving to a very warm climate in the Caribbean, and so they're there safely. Just they don't need the fur. Are you saying my story's not true? So
I thought you were gonna say because they were already dead.
that would be cruel. All right, so basically what I'm doing is I'm rubbing these two objects together, in case you couldn't tell from looking. I'm transferring electrons from one side to the other. Which one gets electrons? Which one is giving up electrons?
The PVC is getting it up.
Why do you say that?
Because previous knowledge, static electricity, like when you have socks on and like wool carpet, you get the energy into your sock, and then when you touch something, you get shock. Does that make sense?
Why do you, so if I, let's say this is shag carpeting and I rub wool socks or whatever across the carpet, and I go for the doorknob, I get shocked. Which way does the spark go?
From you to the doorknob? Or does it go from the doorknob?
That's a good question. That would probably answer this one here to some extent. Because if they're both charged, if I become positively charged and I go for the doorknob, electrons are going to jump to me because it's electrons moving. Or if I become negatively charged, that means I have excess electrons and I go to touch it and the spark's going to go the other way. Actually, I'm not sure in that case. But this one I am a little bit clearer on. Actually, the rabbit fur is giving up electrons. So if I do that enough, then, of course, it's a physics demonstration, so flip a coin whether this will work or not. This is negatively charged, this is positively charged. As I bring it closer to it, what happens to the leaves?
They move apart.
Why?
Because of the charges are or the same.
Because the charges are the same. Let's flesh that out some.
So when you put the, I guess, would it be, is electricity a force? Is electricity a force?
Well, let's actually address that. What is electricity?
Just,
A force of lightning.
is it just electrons?
All right, let's back this up to a 151 question. For those of you who had me before, what's gravity?
Acceleration due to gravity.
Acceleration.
It's a force.
Really?
Oh. Acceleration due to gravity is your weight. No.
You're saying some key words there. Just there were some there were some connecting words that made it seem like you don't remember anything from a couple of weeks ago. All right, gravity is a huge topic. That's what this gesture is. Gravity is a huge topic. We only look at some small aspects. We look at the acceleration due to gravity, we look at the force due to gravity, we look at the gravitational constant. These are all small aspects of a very large topic. Electricity is a very large topic of which we are looking at very small parts of it. So, I can't really define electricity other than it's a very huge topic taking into account, in essence, charges and their movement. And relationship to each other. All right, so let us assume this is negatively charged. I bring it closer to there, the leaves move apart, I pull this away, and the leaves go back to where they were. Because the leaves go back to where they were, we can assume that no charges were transferred. So, why do the leaves move apart as I bring it closer but don't touch it? Don't forget your two rules here.
Well,
Because they're both electrons.
Pardon?
Is it because they're both electrons, so they're both negatively charged?
Let's work on that.
So is it like, right now it's neutral, but if you move the pipe closer, both of the leaves get electrons, and since they're like, they repel from each other?
Where do they get the electrons?
Pipe. The pipe.
From that?
Yeah.
Let's assume nothing transferred. I'll show you what happens when they do transfer, but it's safe to assume that no electrons came off of that onto this.
Then is it the other way around?
Let's go with no.
so is it kind of like where the presence of the negative charge decided to, like, that presence affected them, but when the presence is removed, they go back to normal?
Okay. Yes, but let's make sure we know what that effect is. Why does bringing a negative charged thing towards this, what effect is that going to have? Besides the leaves move apart.
It's essentially letting them have both a negative charge.
Is it transferring to the other?
No transfer. Unless you're talking from the PVC to this, no transfer. It has to be closer, or that has to be really charged. All right, so if that's neutral, what can you tell me about the electrons in this at the moment?
There's none. There's none.
Oh, I hope there's some in there. Yes, there are electrons in there. You yourself made the claim that it was neutral. Neutral being just as many positive as negative charges.
Oh, so when you added the more, so essentially there's now more, when the thing is now, well, English. So PVC pipe comes towards the thing.
Yes.
It's not transferring it, but there's now more electrons in this field, and so because there's more negatively charged electrons, they repel off of each other.
What's getting repelled? So I'll talk about in terms of this one right here.
But because there's more.
Okay, the negatively charged thing right near it.
Yeah, it's not transferring, but there's now more in that space, so the two electrons are now repelling off each other.
Okay. Oh, you're stopping there?
Half baked, but you know.
Let's say I've got a block. Oh, it's this one again. Oh, it magically changed. I've got a block of something here, and let's say it's neutral. What can you tell me if it's neutral? I just made a comment about that, but if it's neutral, what can you tell me about positive and negative charges in this thing? All right, so plus minus, plus minus, plus minus, minus plus, plus minus, minus plus, plus minus, plus minus. All right. To draw all of the ones in any object that size, I would die of old age before I finished. So we'll just, this represents all the pluses and minuses. If anything moves in here, let's assume that the block stays, the center of mass of the block stays where it is, it's a rigid object. If I bring a negatively charged object near it, what is going to move over here?
The electrons.
Okay, so which way will the electrons move if I bring a negatively charged thing near it?
Away from the negatively charged thing.
Say it again?
Move away.
All right, so these electrons would suddenly start moving over to that side, so it would look, you'd have primarily electrons over there, and then you've got positive charges still distributed evenly throughout.
And so because in that, the presence of the PVC pipe, those two, you have these two objects, and so because it's coming from here, the two dangly thing, to the two leaves, their electrons move towards the right and then towards the left, and so because now both of their electrons are on this facing each other, it's two negative charges, so the negatives repel, thus causing it to go like that.
Where are those electrons coming from?
Those electrons are coming from the PVC pipe.
No.
Are they already in there? Just the ones that are already existing
Where?
inside the leaves?
The electrons are inside the leaves now and they're not repelling.
Well, yeah.
Isn't that the pipe pushes them away from the leaves and all that's left in the leaves are the positive charges?
No. What's left in the leaves should be negative charges.
Is it the?
Or, sorry, badly worded. There should be an excess of negative charges in the leaves. But where do those excess of electrons come from? It's not the pipe.
The connector bit?
The what?
The conductor?
Okay, the knob. So basically, as the negatively charged pipe comes near it, those electrons that are here run away. Well, the only place to go is the leaves. So basically, we get excess electrons because they're being chased away from here. As the threat is removed, the electrons can go back home. The Mongol hordes come in, and then they leave. People go back to their way of life. The electrons go back to their way of life. Let's only personify them so much. So then it becomes neutral again. Everyone's happy. Now, what's going to happen when I touch the PVC to the knob?
I would assume the leaves would flare the same direction but farther out.
Okay. Anyone have a different theory? Or do we want to risk public humiliation for Jack by himself?
I think it's either gonna be that or the complete opposite. It's one of the two.
What would be the complete opposite, that they
They
go
just like smash together.
dash together? To do that, what can you tell me? If the leaves match together, what would have to be true?
One would have to be negatively charged and one would have to be positively charged.
Yeah. And these are